In this chapter, let's talk about some of the commonly seen and used distributions. Okay. Let's before we talk about discrete distributions, let's talk about the random variables. What is random variable? A random variable is a function or rule that assigns a numerical value to each outcome in a sample space of a random experiment. We talked about a random experiment and sample space in the previous chapter, chapter 5. Right? There are some nomenclature issues here. We normally use capital letters, such as capital X, capital Y, to denote, represent random variables. We use lowercase letters, such as lower x, lower y, to represent values of that random variable. Okay? And the discrete random variables has a countable number of distinct values, as we know already. Okay. Probability distribution. What is probability distribution? A discrete probability distribution assigns a probability to each value of a discrete random variable. So, for example, if we have a discrete random variable, such as number of heads of flipping a coin, if we assign the probability to that head or to the tail, then we are actually formulating or establishing a discrete probability distribution. To be a valid probability, each probability must be between 0 and 1. That is, Pxi is less than or equal to 1 or larger than or equal to 0, as we talked about before. And the sum of all the probabilities for the values of x must equal to unity. That's because if we add up all the probabilities, they must add up to 1, because that includes all the possible outcomes. That's the total sample space. Okay. Let's take a look at an example of flipping coins, coin flipping. Okay. When you flip a coin 3 times, what will be the sample space? We basically have a sample space that has 8 equally likely simple events. They are: the first toss, you could get head; second toss, head, head; or first toss head, second head, the third is the tail, or the HHT, or HTH, or HTT, or the first one is tail and then head, head, THH, THT, TTH, and TTT. Right? That's all the possible outcomes of the sample space when you flip a coin 3 times. Right? Now, what is the probability? What's the chance of getting the head? 1 head, or 2 heads, or 3 heads? Right? We can count them. Okay? Now, if x is the number of heads, then x is a random variable, whose probability distribution is as the following in this table here. The probability of x equals 0 with no 0 heads occurs when you have 3 tails right here, 3 tails. And we know, if you look at this chart here, you have 1 out of 8 possibility here, in this one here. Okay? So it's 1 in 1/8 of probability. The chance of getting 1 head occurs when you have a head, tail, 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 head, tail, or tail, tail, head. So in the 3 of them. So the probability of that getting 1 head, x equals 1, is 3 out of 3/8. Right? Same token, the probability of getting 2 heads is 3/8. Getting 3 heads is 1/8. Right? And you add them all together, 1/8 plus 3/8 plus 3/8 plus 1/8, you get 8/8, or you get 1, because that's all the possibilities. Okay? Now, if we plot them on the chart, that this number of heads, or x, the random variable here, is 0, 1, 2, or 3 heads. And the probability, as we just calculated, and the probability of getting 0 heads and 3 heads is actually the same. Getting 1 head and 2 heads are also the same. Now, this is the probability distribution, a discrete probability distribution of the coin flipping 3 times. Okay? Note also that the discrete probability distribution is defined only at the specific points on the x-axis, because that's only numbers they can take. Okay? Then let's introduce the concept of expected value. The expected value EX of a discrete random variable is the sum of all the X values weighted by their respective probability. What do we mean by that? This is the equation for expected value of X. EX equal, we also use mu, the Greek letter mu, to denote that. If you recall, we use mu for the, what is it for? It's for the mean of the population, right? Now, why do we use that for the expected value? We explain that just a minute, right? The mu, or expected value, is the big sigma here, means the sum, add them all up from first one to nth one, xi, the individual x values, times pxi, the probability associated with each and every one of those x values. So basically, just x times px added up, that's your expected value. This is also the mean, right? And this is a measure of central tendency. If you remember what the central tendency is about, it's the value around which the numbers are distributed. Okay? Let's look at example here. That's service calls. In this appliance store, appliance repair shop, right? Ace appliance repair shop. The probability distribution of emergency service calls on Sunday is like this. Basically, there is a 0.05 probability or 5% chance they will get zero service calls on Sunday. There's 10% chance they get 1 call, 30% chance they get 2 calls, 25% chance they get 3 calls, and 20% chance they get 4, and 10% chance of getting 5 calls. And these all the probability together is 1, but that's because that's all the possibilities. For this repair shop, they get, at the least they get 0 calls, and most they get 5 calls, and that's all, right? So what is the average or expected number of service calls? Because what is the expected value or average? We know that the probability by each, right? But what is the average? To calculate the average, we actually calculate the expected value. Okay? How do we do that? We know the number of calls right here. We know its associated probabilities in this column here. And then we use 0 times 0.05, we get x times px. 1 times 0.1, we get 0.1 here, 0.1 here, xpx. 2 times 0.3, get 0.6. 3 times 0.25, get 0.75, etc. And you add all this column is 2.75. Remember, the expected value equals mu, or we call it mu, or mean, and this sigma, big sigma, sum up from the first one to the fifth one. Why is the 5 here? Because we have from 0 to 5, right? And xi times pxi. Okay? And actually, this should be 6 here. There's a little error here. This should be 1 through 6, because we have 1, 2, 3, 4, 5, 6 observations. Right? And if we add up all these here, this column right here, that's exactly what this equation is about. So the expected value is going to be this red number, 2.75. Okay? 2.75. So this 2.75, this particular probability distribution, is not symmetrical around the mean though. 2.75 right here. Okay? This is the distribution of different calls, and this is the 2.7% mean. We call this point, this is the balancing point, or fulcrum point, where it's the mu, where it's the average, where it's expected value. They're all the same thing. Okay? So because EX is an average, it does not have to be an observable point, because you cannot really have 2.7 calls. So that's the probability. Now, why is it called the average or mean? If you look at that, when we calculate the mean of a population, how do we calculate it? Right? We actually add up all the values and divide by its probabilities, right? But excuse me, let me repeat. We actually add up all the values of x divided by the total number of values. That's n, right? In this case, if they are the same, all of them have the same opportunity or same probability of occurring, the Pxi will be 1 over n. In that case, this will simply be the sigma of xi over n. And that's exactly the definition or the way the equation to calculate the mean. That's why you can see that the equation that we use to calculate the mean is just one special case of this expected value. Okay, let's move on. Variance and standard deviation. Right. Then if there are n distinct values of x, then the variance of this discrete random variable x is, we call it variance. X is sigma squared, little Greek letter sigma squared, and it equals xi minus mu squared times pxi. Okay? And basically this is the weighted average of the dispersion about the mean, and it's denoted either as sigma or Vx. Right? And what's standard deviation? Similar to the standard deviation definition we had before, is a square root of the variance. Of course, square root of sigma squared is a sigma, and the square root of Vx, the variance of x. That's how we call the variance, calculate the variance. Let's take a look at another example here. There is a Bay Street Inn that's a 7-room bed and breakfast in Santa Teresa, California. The probability distribution of room rental during February is this. Basically, they have a 5% chance of have no room rented. Nobody comes. The 5% chance there's only one room rented, one customer. And maybe there's a 6% chance they have 2 rooms rented, so on and so forth. Add them all up, that's 1.0, that's 100%, because they have a total up to 7 rooms, right? They could have 0 room rented to up to 7 room rented, or to all the rooms rented. Okay? Now, how do we calculate the mean? We already know that, right? We can calculate the expected value, or we can calculate the variance and standard deviations, right? We can calculate expected value. We can actually calculate from add up x times px in this column, add all up, right? This should be 1 through 8 actually. There's a mistake here again, right? And that we know is 4.71. That's the expected value of the average. On average, they will have 4.71 room rented during the month of February. Okay. Now, how do you calculate the variance then? The variance simply is, okay, we have x times x px, x times px. We need to find x minus mu squared. Well, x minus mu squared is this number 0 minus mu. Mu is here 4.71. Look at here my cursor, right? The difference squared, that's 22.818. That's for this column. If it's this row, then for this row, x minus mu will be 1. There'll be 1 minus mu, 4.71 squared. And then this column, 2 minus mu squared, and so on and so forth. We can calculate all 7 of them, or 8 of them. Then x minus mu squared times px will be this value, this column here, times this column px. 0.05 times 22.18 give you 1.1, and so on and so forth. You add all this up, that's 4.2259. That is the variance. And what is standard deviation then? You take a square root of 4.225, you get a standard deviation. Okay, very simple. 2.0577 rooms. Okay? That's in bed and breakfast. We can also put a histogram to show, excuse me, let me close door here, to show the distribution, and this seems to be skewed. In this case, the long tail to the left, so it is skewed to the left. That's number of room rented and its associated probabilities. Okay? The mode is 7 rooms rented, but the average is 4.7 room. 7 room rented because the mode is 7, because that's the most occurring one, so they seem to be having good business there. Right? It's mode, and this is a 4.71. This is the mean, right here. This is the mode. This is the mean. Okay, a sigma of 2.06 indicates a considerable variation around the mean, around the mu. Okay. Basically, when we construct a distribution chart, we can have a PDF or CDF. PDF is a probability distribution function. That's a mathematical function that shows the probability of each x value. A CDF, or cumulative distribution function, is a mathematical function that shows the cumulative sum of probabilities, adding from the smallest to the largest one, x values, gradually approaching unity. Let me explain that to you. Like this one here. If this is the value of x, this is the probability of each, and if you draw a chart, and that's the probability distribution function. And how do we construct the CDF? That's PDF. How to construct the CDF from this? For the CDF, the first one is the same as the first one here. For the second one, it will add up the first two. For the third one, we add up the first three. Fourth one, we add up the first four, etc. We keep adding them up, and so of course the probability will go up. Cumulative probability will go up, up, and curve approaching 1, and finally reaching 1 right here, the last observation. Okay, that's the CDF, cumulative distribution function, versus PDF, probability distribution function. Okay. All right, let's talk more about uniform distribution, because that's the the simplest form of distribution. CDF, uniform distribution. A uniform distribution describes a random variable with a finite number of integer values from A to B, the only two parameters, A and B. A is the lower bound, B is the upper bound. Each value of the random variable is equally likely to occur as uniform. And let's consider this following sum of uniform distribution. This is the summary of the uniform distribution. A is the lower limit, B is the upper limit. The PDF is Px is 1 over B minus A plus 1. I don't expect you to know how to arrive at this. It's just to know the equation, to know where to go to find it, or which one to use. That's good enough for this class, right? The range is between A and B, and the mean is A plus B divided by 2, and standard deviation is B minus A plus 1 squared minus 1 divided by 12, and the square root of that, right? And the random data generation in Excel, you can use this to do that, and you can use this as a benchmark to generate random integers or to create other distributions. A good example is rolling a die. The number of dots on the row of die form a uniform random variable with 6 equally likely integer values, 1, 2, 3, 4, 5, and 6. Right? Now, what is the probability of the rolling a die? Rolling one of this is the PDF. For each one of the 6 numbers, 1 through 6, we know the probability is 0.166667. So they're all the same. Now, with the CDF of that, the first one here is 0.1667. The second one is 1.667 plus 1.67. The third one keep adding up until the last one is 1.0. Right? That's the CDF for a die, rolling a die. Okay. Let's look at the PDF for a rolling die. Is Px 1 over B minus A plus 1. In this case, B is 6, A is 1. So B 6 minus 1 plus 1 is 6, is 1 over 6. We already know that. The mean is A plus B divided by 2. 1 plus 6 divided by 2 is 3.5. And the standard deviation, we plug in the number, will give you 1.718. That's for a uniform distribution. Now let's talk about another distribution called the Bernoulli distribution. Basically, what is a Bernoulli distribution? That's a random experiment with only 2 outcomes. That's called the Bernoulli experiment. And if you flip a coin, you have 2 outcomes, right? You have a head or tail. That's Bernoulli experiment. One outcome is arbitrarily labeled as success. Now, this has nothing to do with the success or failure in ordinary society. We just call it success, right? We denote that as x equals 1. And the other is a failure, x equals 0, 0 and 1. Failure and success. And pi is the p success, or the probability of success. 1 minus pi is probability of failure. If normally success is usually defined as the less likely outcome, so the pi is normally minus less than 0.5 for convenience. Of course, in the case of flipping a coin, we know the P success is 0.5, P failure is 0.52, because we get 0.5 chance of getting either head or tail. Right? Now the P0 plus P1 is 1 minus pi plus pi equals 1. And pi, of course, is as probability has to be between 0 and 1. That's a Bernoulli experiment. Right? And the expected value of Bernoulli experiment is simply P, if you use xi times P times the probability from 0 to 2, there are only two states and two outcomes. The first one is 0 times 1 minus pi. The second is 1 times pi. And 0 times that is equals 0. 1 times pi is pi. So for Bernoulli experiment, the expected value of mean is simply the pi. That makes it simple. Now what's the variance of that? Right? We plug in the value for the to the equation of variance Pxi minus E or minus mu squared times P. We plug in the xi and the probability, we will get pi times 1 minus pi. That is the variance of Bernoulli experiment. And the standard deviation, of course, is square root of that. Next, let's talk about the binomial distribution. Now, this is more actually the Bernoulli experiment repeated many times, n times. That how binomial distribution arises. Okay, each Bernoulli trial in the binomial is independent, so the probability of success pi remains a constant on each trial. You can imagine this as flipping a coin over and over many times. That becomes a binomial distribution. Okay. In a binomial experiment, we are interested in the number of successes in n trials. So the x equals x1, x2, x3, all the way up to xn. We want to know how many successes, like for example, how many heads we're going to have. Right? That's what we're interested in. Okay? And the probability of a number of success is determined by the parameters n and pi. In this number of trials, pi is probability of success. The mean of a binomial distribution is found by adding the means for each of the Bernoulli experiment. So the pi plus pi plus pi, there are a total of n of them. So the mean is n times pi. The variance is pi times 1 minus pi plus pi minus 1 minus pi. Keep adding up all n times. What you get is n times pi times 1 minus pi. That's variance. And the standard deviation, of course, is just the square root of this right here. Okay? That's the binomial distribution. This table summarizes all the properties of binomial distribution. N is number of trials. Pi is probability of successes. This is the PDF. This is how you get it from Excel. This is the range. This is the mean. This is standard deviation. Okay. I just want you to be able to use this function, use those equations when you come across a binomial distribution type of question. Okay. You will get more concept, more idea about this as we work on the review questions, actual questions. Let's take the example of oil change shop. It's important to quick oil change shop to ensure the car's service time is not considered late by customers. You know, like for example, how much time do you need to change oil? You know, if it takes more than 30 minutes, some people may feel that it's late or it's delayed. The service times are defined as either late or not late. Right? If X is the number of cars that are late or the total number of cars serviced, and then we can assume that the cars are independent of each other. Right? It's not that they're going to keep one car, specific cars longer than others. You know, they're not dependent on each other. And the probability of a late car is consistent. Then what is the probability that exactly 2 of the next n 10 cars serviced are late? In this case, P, the probability the car is late, is we know is 0.1%, 10%. Pi is 10%. And the car is not late is 90%. So then 10% of cars are late. Okay. So now that the probability distribution function is this for binomial. Okay. And then if we plug in the numbers, n in this case for next 10 cars, n is 10, the 10 factorial, x is 2,
n minus x is 10 minus 2 squared. Pi is 0.1 squared, x is 2. 1 minus pi n times n to the n minus x power. Okay? If you carry out this calculation, you get 0.1937. That is the probability that exactly 2 out of the next 10 cars are late. Okay? Let's look at another example here. On average, 20% of emergency room patients at the Greenwood General Hospital lack health insurance. They don't have health insurance. Right? Of course, this is before Obamacare was in place. In a random sample of 4 patients, what is the probability that at least 2 will be uninsured? Right? If you use X to denote the number of uninsured patients, or success, kind of that's sarcastic, and then the probability of uninsured is pi, that is 0.2. So 20% don't have it, right? Then the probability that people do have insurance will be 1 minus 0.2 is 0.8. Okay? The N is the 4 patients, right? So the range is from 0 to 4 patients. Now, what is the probability that at least 2 will be insured, right? And individual probability can be added to obtain any desired event probability. For example, the probability that the sample of 4 patients will contain at least 2 uninsured patients is what? What is the, let me ask you a question here. What inequality means at least? Right? If at least 2 means what? The x equals 2 is at least 2. 3 is at least 2. And 4 is at least 2 as well. Right? We can calculate that the px equals 2 is 0.15, p3 is 0.02, p4 is 0.0016. So the total is 0.1808. Okay? Now that's the probability of at least 2. Now what is the probability that fewer than 2 have insurance? What is fewer than 2? If there's no one, zero number of people having insurance, that's fewer than 2. If the 1 person having insurance, that's fewer than 2. Right? So basically we need a probability of P0 and P1 to get fewer than 2. Right? Fewer than 2. And that is 0.4096 plus 4.96, that's 8192. Now what is the probability of normal than 2? Now what is meant by normal than 2? Normal than 2, if it's 0 was normal than 2, right? So 1 is normal than 2, and 2 is normal than 2. So we can just add up the probability of 0 and 1, 0 and 1 and 2, we get normal than 2. Okay? So this sometimes it's helpful to sketch a diagram like this. From here on, this is at least 2. Fewer than 2 is from this point on, fewer than 2. This is fewer than 2, and this is more than 2. Okay? So what does the mean and standard deviation of this binomial distribution? We know the mean is n times pi, so 4 times 0.2 will give you 0.8. Standard deviation is n pi times 1 minus pi, the square root, and so we may take a radical of that, that gives you 0.8. Okay? Let's talk about another distribution. It's called the Poisson distribution. This is actually also called the model of arrivals. The most Poisson applications model arrivals per unit of time, such as you're at the train station. What's the number of people arriving at the train station in the morning? That arrivals, model of arrivals, follow the Poisson distribution. The event occurs randomly and independently over a continuum of time or space. Because if this is time for a flow of time axis, this is a unit of time, another unit of time, another unit of time, right? And each dot is occurrence of the event of interest, and we want to know the number of arrivals in a given unit of time. If we use x to denote the number of events per unit of time, then x is a random variable that depends on when the unit of time is observed. Okay? For example, if you could get x equals 3 or x is 1 or the 5 events, depends on where the randomly chosen unit of time happens to fall. Right? You can choose this, or that. Okay? In the Poisson process, there's only one parameter called lambda, the Greek letter lambda. Lambda represents the mean number of events per unit of time or space. The unit of time should be short enough that the mean arrival rate is not large. Normally, when we say not large, that's less than 20. Okay? And Poisson distribution is red skewed, right? But becomes less skewed and more bell-shaped if lambda increases. And these are the equations for the Poisson distribution. This is the PDF. You do not need to know how to arrive at this. You just know which equation to use. The mean is simply lambda. Standard deviation, the square root of lambda. That's it. Right. Let's take a look at the example here. For Poisson distribution, we need to use table, and the table is in the back of your book. Right. Let's see, for this the credit union customer example. Okay. On Thursday morning between 9 a.m. and 10 a.m., customers arrive and enter the queue at this Oxnard University Credit Union at a mean rate of 1.7 customers per minute. And what does the PDF mean and standard deviation then? Right? The PDF from the equation is this. We plug in the number, lambda is 1.7, right? That's the PDF. The mean is 1.7, right? And the standard deviation is sigma, the square root of 1.7, right? Or it's 1.3 customers per minute. Okay? Now here is the Poisson probability distribution for lambda 1.7 customers on average, and know that this is the number of customers. This is the probability distribution for each of them according to the equation we just looked at. And this is the probability of no customers, one customer 1.31, two customers 2.26, etc. And this is CDF. This is calculated by the first one is the same. The second one, 4.94932, equals this one plus this one. And third one here, CDF, equals all three added up. Fourth one, 0.90768, equals all these added up, etc. Okay, that's the probability here. Okay. For example, Px equals 4 is the probability that there are exactly 4 customers in the bank. There's a 6.06 or 6.36% chance that exactly 4 customers will be in the bank. Okay. Now let's look at some compound events here. Right. Cumulative probabilities that can be evaluated by summing individual X probabilities. Here's the cumulative probabilities. What is the probability that the 2 or fewer customers will arrive in a given minute? Remember here, 2 or fewer. What is 2 or fewer? 0, no customer is 2 or fewer. 1 is 2 or fewer. 2 is 2 or fewer, right? So for P2 and fewer, then we just add up P0, P1, and P2. And we know from the previous table the value of P0, P1, and P2. We just add them up to 0.7573. Okay? Now, what is the probability that at least 3 customers are in the event? Are there? What is at least 3? Think about what is at least 3. How is that related to fewer than 2? So if fewer than 2 and at least 3 or more, aren't they complement of each other? Yes, they are, right? You can either have fewer than 2. If you had them more than fewer than 2, there's a more than 2, you're going to have at least 3. So for the probability of at least 3, you can simply use 1 minus the fewer than 2, Px minus equal 2. And that gives you, 1 minus 0.7574, that's 24% chance. Okay?